So for question 2, we are given the following HMM, and essentially our goal is to kind of use the forward algorithm to derive the forward algorithm for our model right here. And what we have here is essentially this h of t, which corresponds to our hidden state, and then each of these e of t and r of t, which correspond to our observation states or our evidence states. So both of these are observable. And the key difference here from our vanilla HMM is that we have a second observable state, and we have this dependency right here, where r of t, or sorry, h of t plus 1 is dependent on the previous r of t. Okay, so that's just like a couple things to keep in mind. Let's dive into the parts of the problem. And so a lot of this is like kind of vanilla, just like flavor text. So I mean, I encourage you to parse this in gathering the correct information. If you're interested in figuring out like ways to parse this, I'd recommend just like highlighting, okay, T of RT, evidence ET, and then you know that those two are the evidence variables. And then just caused by the human action H of T. And then we can see that based on our HMM model right here, H of T is the hidden state variable, whereas the E of T and the R of T are the observed. Okay. And we are also given the following probability tables, and each of these kind of just are associated with the nodes in our HMM. So that shouldn't be like too crazy. This right here is the prior distribution of H0. R of t given ET and ET given HT correspond to the sensor model, and H of t given HT minus 1 comma RT minus 1 corresponds to the transition model. And so we use each of these in the traditional HMM as well. The real main difference is that we have two probability tables for our sensor model. Okay, so now our goal is deriving the forward algorithm using our two components, the time-elapse update and the observation update. And essentially, following the standard procedure, we would usually do the time-elapse update first, and then we would do the observation update to incorporate our evidence. In this problem, they want us to start with the observation update and then go to the time-elapse update. So we'll do it that way instead. So in this case, if we want to incorporate the evidence at time t, so right here, using our time-elapse update expression, we are given this following value. So this is our result of running the time-elapse update. Oh, no, not this. This is our result of running the time-elapse update, where we're given some sort of probability ht, given e0 to t minus 1, r0 to t minus 1. And what we want to find is this value, which is the observation update. And this is the probability of ht given e0 to t and r0 to t. So notice right here, it's kind of the same thing as the time-elapse update, except we're incorporating evidence from the next time step as well. So the question right here asks us to, assuming that we've already calculated the correct time-elapse update, we want to figure out the options that make valid independence assumptions and would evaluate to the observation update expression. So really, we're just trying to use probability rules to find expressions that are equivalent to this one. All right, so let's start. The first thing that we would usually do when we have a conditional independence assumption, or sorry, not conditional independence assumption, a conditional probability, is to break it down using Bayes' rule. So recall that Bayes' rule just says that a conditional distribution of like A given B, for example, is just going to be the probability of the joint of A comma B over probability of B. So just divide the joint distribution by the probability of the things that are given. And so we can basically rewrite this expression of O of H of t. So O of H of t is just going to be equal to the probability of ht given E0 to t comma R0 to t. And then using Bayes' rule right here, we can break this down into just P of ht comma E0 to t R0 to t divided by the probability of E0 to t comma R0 to t. Okay, and let's just recall from the traditional observation update formula that when we want to calculate our O of h of t, or for example, P of h of t given E0 to t, comma R0 to t. This value is proportional to the value of the time-elapsed update, right? So we take the time-elapsed update, in this case is th of t, and then multiply by our probabilities associated in our sensor model or our observations. So in this case, our observations consist of these two CPTs, probability of RT given ET, and probability of ET given HT. So essentially, this value is going to be proportional to T of HT times probability of RT given ET. Oh, I should be using lowercase. RT given ET, and probability of ET given HT. And so replacing this in our equation gives us the following, where we have our original conditional independence assumption is just going to be equal to P of HT given E0 to t minus 1, R0 to t minus 1, times the probability of RT given ET, times the probability of ET given HT. And this is all divided by the probability of E0t, comma R0t, which is the same as taking the joint distribution that we have on top and summing out the h of t variable. In this case, I can just say we can sum over the values of ht, where we get p of rt, comma et, p of ht, comma e0 t minus 1, r0 to t minus 1, and p of et given ht. So just to reiterate, this right here corresponds to the time-elapsed update like this. And then the rest are just following one-to-one. And what we did is we took what we know is our joint distribution. And we know our joint distribution is basically proportional to our conditional distribution, right? And this is how we basically found our conditional distribution, where we normalized by dividing over the same joint distribution where we summed out h of t. And so as we can see, the top and the bottom are the same, except all we have here is we have a sum where we sum over the h of t. And from here, we have an answer that looks pretty similar to some of our options. And from there, we can kind of just like go through our options and see which of those are equivalent. So for the first one, we see that this is directly the same, so we can just kind of bubble that in. In the second one, we see that all we did was get rid of the RT given ET, and notice that we can actually bring this out of the summation because it doesn't contain any terms with HT in it. So it's just like the same as multiplying by a constant, in which case we can just cross that off from the top and the bottom, and we would get that answer right here. So that works as well. And the rest, if you try to simplify this any further, you won't have a way to really get rid of the bottom. And the last expression also doesn't work as well. So in the end, we just have these two as our answers. And so, yeah, so at the top right here, we have some sort of summation on the top over ET, which doesn't really work either. And we have this ET given RT minus 1, comma HT minus 1, which is also just like not part of our expression either. So that's why that one doesn't work. All right, so let's move on to part B. In part B, we have the same HMM, and what we're asked to do is find the time-elapsed update. And what we have right here is the observation update from our previous time step. So O of HT minus 1, which is essentially just the probability of HT minus 1 given all of our evidence from the previous time step. And we want to compute basically the result of running the time-elapsed update on this probability. So in general, when we're trying to construct the time-elapsed update, what we want to do is we always have basically three main parts that we want to consider. I'm just going to go back to front because I think it makes more intuitive sense. But for the first part right here, what we would want to include here is some sort of recursive step. So what the recursive step means is we take just like the probability from the previous time step, right? So for example, if we are running some sort of time elapse update, we have to start somewhere, and that would be from our result of running the observation update from the previous time step. And so that like allows you to go in sequence and kind of just like keep operating on like the same probability and like kind of propagate the values. So what we want to consider is the recursive step. The next thing we want to consider is the transition model. And the transition model is just the probability of the probability associated with advancing from the previous state's values to the next state's values. So that's straight up from the table where we have, like, for example, the probability of xt plus 1 given xt is the probability of taking that next time step forward from like a hidden state. And then the last thing we want to consider at the front is we need to sum over all variables we don't need. And this will be more clear once we write the rest out. Okay, and let me just move this to the side right here. Okay, so let's just start with the recursive step. So the recursive step is just asking for the value at the previous time step. And in this case, we have this given to us right here. Normally, we would write this as just like the probability of ht minus 1 given e0 t minus 1, comma, oh, let me just move this over, comma r0 to t minus 1. Right, and this was just our O of ht minus 1. So this is like the probability that we start with before we want to multiply by our transition model. Okay, and so now we want to multiply by our transition model. And so what that means is essentially we need to look at our hidden states. So for example, in this case, our problem only contains this hidden state, ht. And we want to multiply by the probability of going from essentially that previous hidden state to the next hidden state. And in this case, we're given this CPT right here, probability of ht given ht minus 1 comma rt minus 1 to be our transition model. So in this case, we just multiply by this. So p of ht given, oh no, okay, ht given ht minus 1, rt minus 1. And so notice, like, if we were just to look at this BaseNet, for example, we could see that the CPT at like ht plus 1 is going to be probability of ht plus 1 given ht comma rt. So it's like the same thing. So that right there is our transition model. And then lastly, what we need to do is we need to sum over some certain variables that are not needed. And how do we know what's not needed? Well, we can take a look at the variables on this right side. And then we can take a look at the variables on this left side and just sum over the variables that are not on the right, but are on the left. So in this case, the one variable that is not present on the left, but is present on the right is actually ht minus 1. So what we need to do is sum over ht minus 1. And just to clarify that I'm summing over, I'm just going to make all these lowercase so that we know that we are summing out that particular variable. All right, and that's the answer. So this is kind of how you would approach the same kind of mindset when you're asked to derive the time-elapse update as well as the observation update. And then just breaking it down into these 3 steps will really help you in kind of figuring it out if you're kind of getting stuck on like the nitty-gritty of multiplying probabilities together. But yeah, that concludes problem 2. So thanks so much for watching and see you all next week.